Hello students, welcome back to lecture 31 of this course. In the last lecture, I started discussing about NMR and its principle. In this lecture, I will discuss about how to process the NMR data. Then we will discuss about chemical shift and the factors affecting chemical shift. In the last lecture, I showed you that signal in NMR is given by this equation. S at a given time is equal to S naught multiplied by exponential I, and this is capital omega, which is basically chemical shift multiplied by time multiplied by exponential minus R2 into T, R2 into T. So, this signal is called free induction decay, and it will look like this. If I plot S versus T, it will look like this. This is known as free induction decay or FID, and it is basically a time domain signal, time domain signal. So, in NMR, we generally start with time domain signal, because that way we can maximize the sensitivity. You must remember that NMR is low sensitive technique, because the gap between ground state and excited state is very low, and that means that population difference between two states are quite small. Population difference between two states is quite small, and hence the sensitivity is low. So, one of the things which we do is to get the signal in time domain and then do Fourier transformation. So, if we do Fourier transformation of the FID, what we are going to get is two different peaks, which is one is called absorption and the second is dispersion. So, if we take Fourier transformation of this signal, what we are going to get is A, which is a function of omega, is equal to R divided by R square plus omega minus capital omega square, whereas d omega is given by minus omega minus capital omega divided by R square plus omega minus capital omega square. So, this is your absorption and this is your dispersion, and they have Lorentzian line shape. Absorption line shape is always positive, whereas dispersion line shape has positive and negative part, positive and negative part. Now, some important facts about absorption and dispersion peaks, that if you take height of the peak at omega is equal to capital omega, then S omega will be 1 by R, and you can do it here. So, if I take omega is capital omega, then this part is going to be 0, and so A omega is R divided by R square, which is 1 by R. So, and the second thing is, if I take S omega is equal to 1 by 2 R. So, in that case A omega is 1 by 2 R, and this is equal to R divided by R square plus omega minus capital omega square. And so, what does that means is 2 R square is equal to R square plus omega minus capital omega square. So, R square is equal to omega minus capital omega square. So, R is equal to plus minus omega minus capital omega. And what does that mean is omega will be equal to capital omega plus R and or capital omega minus R, capital omega minus R. And so, the difference, so if you remember that peak looks like this. So, this height is 1 by R, and that is what is written 1 by R, because at this point omega is equal to capital omega, and if I take this omega half, it means at the half height where signal is equal to 1 by 2 r. So, this is 1 by r. So, this will be 1 by 2 r. So, this value is given as omega minus r, and this value will be capital omega plus r, and so difference between these is 2 r. So, width at half height means when signal is 1 by 2 r, then width at half height is, this width is your this plus omega plus r minus this minus plus r. So, this cancels out. So, this is equal to 2 r. So, equal to 2 r. So, this is characteristic of absorption and dispersion peak. Now, let us think about that if we take a small some molecule which is a complex molecule, it is going to have various types of protons. Hence, FID will be superposition of various frequency and each having a different decay rate. Okay, so now question is, we have to apply pulse at one time. Suppose I am applying 90-degree pulse to get a 1D spectra, and which kind of pulse we should use, because there are several resonances in NMR spectrum of a molecule with different Larmor frequency, and it is not possible to be on resonance with all the lines. So, we have to choose a transmitter frequency such that we are affecting all the resonance at the same time. So, if you are looking at proton spectrum, it covers about 10 ppm, it goes from 0 to 10 ppm. So, in that case transmitter frequency is generally put at 5 ppm. Thus, the maximum offset is 5 ppm on both sides. So, 0 to 10 ppm, suppose this is your NMR spectral region. So, I generally put my transmitter frequency at 5 ppm. So, offset on both sides is 5 ppm, which corresponds to 2500 hertz on 500 megahertz NMR spectrometer. So, 500 into 5 is equal to 2500. This is equal to 1.6 into 10 to the power 4 radian per second. So, 2 pi into 2500 is equal to 1.6 into 10 to the power 4 radian per second, and for that generally we apply 90-degree pulse of around 12 microsecond, In that case omega will be your pi by 2 divided by your time of the pulse, since so basically omega t is equal to theta, and so omega is equal to theta by t, omega is equal to theta by t. So, theta is pi by 2 and t is your 12 into 10 to the power minus 6. So, which is around 1.3 into 10 to the power 5 radian per second. So, 12 microsecond pulse is so chosen such that RF field is about 8 times the offset. So, offset is, look, offset is here 1.6 into 10 to the power 4 radian per second, whereas omega 1 chosen is 1.3 into 10 to the power 5 radian per second, and so RF field which is proportional to omega 1 is about 8 times. So, 1.3 into 10 to the power 5 divided by 1.6 into 10 to the power 4, it is around 8 times. So, RF field is about 8 times the offset, and so the pulse can be regarded as strong over the whole width of the spectrum, So, if you want this pulse should be taking care of all the offset, then you have to choose hard pulse which has a small time which is around 12 microsecond, and that kind of pulse is known as hard pulse. That kind of pulse is hard pulse because it is affecting the resonance from 0 ppm to 10 ppm, 0 ppm to 10 ppm, and it is almost around, it will vary from 90 degree to 80 degree, okay, for 90 degree to the resonance which is at 5 ppm and around 80 degree to the resonance which is at suppose 10 ppm. We have to choose a hard pulse such that we can get maximum intensity out of the spectrum. Soft pulse are of higher time, of higher time length, and they are chosen when you want to excite only one resonance, one specific resonance. Then you choose the soft pulse, because soft pulse RF field is very small, whereas for hard pulse RF field is quite large than offset, and so they affect whole width of the spectrum strongly. So, RF field is about 8 times the offset, and so the pulse can be regarded as strong over whole width of the spectrum. So, you want that whole width of the spectrum should get affected as strongly as possible. As strongly means the pulse, your theta should be around pi by 2 for a peaks at 10 ppm or 0 ppm. So, second important thing, if you want to get maximum signal, so it is crucial to use correct flip angles in NMR experiments. You must remember that NMR is low sensitive technique. So, we want to get maximum signal from each scan, and so it is crucial to use correct flip angle, and to obtain maximum intensity we must use a 90 degree pulse, and to invert magnetization we must use a 180 degree pulse. And so, correct length of pulse should be maintained, and therefore, pulse calibration is an important preliminary to any experiment. So, before starting any experiment you must do pulse calibration, because if you are not using exact 90 degree pulse you are going to get a small signal. And the way we do is that we start doing taking a spectra by varying the time of the pulse, varying the time of the pulse. So, for example, we start from 4 microsecond to suppose 48 microsecond, okay, and then get the intensity. So, initially when it is around 0 degree pulse, the time corresponding to 0 degree pulse, you will get no signal, but as the time increases, your intensity will increase, and at 90 degree pulse you should get maximum signal, that is what you expect. At 180 degree you should get 0 signal, and again 360 you should get a 0 signal. So, what you do that at a particular you apply. So, for example, you apply at 4 microsecond, then 5, 6, 7, 8 till 48 microsecond, and then try to see a null condition. Suppose we find a null condition at 24.4 microsecond corresponding to pi pulse, then the pi by 2 pulse will be 12.2 microsecond, and that should be chosen to get the maximum intensity. So, what in the calibration what you are doing is you are applying pulse of different time length, and trying to find out a null condition. And as you know that null condition can be found at 180 degree, 360 degree. So, once you know that this is the time length which corresponds to your null condition, then you know where is 180 degree, where is 360 degree, and once you know time corresponding to 180 degree, you just divide by 2 and then you get the pulse length for 90 degree pulse length for a 90 degree pulse. So, if we find a null condition at 24.4 microsecond, it means 90 degree pulse length should be 12.2 microsecond. Now, let us go to how to process the data, NMR data. It is very important, and again because this is related to enhancing the signal and resolution. So, after you get your FID, you need to process the data before doing Fourier transformation. So, what you can do is, for example, look that we are trying to look at the signal either in x direction or y direction. Suppose we are looking at x direction, and if then I told you that you can get signal at x, you can get signal at y. One will be your x signal will be your cos modulated, whereas y signal will be sin modulated. So, that is what you get. So, signal if at x versus time will look like this, signal at y versus time will look like this, because this is sin modulated, this is cos modulated. And when you do Fourier transformation, this will give you a real signal, and this one will give you imaginary signal. But suppose our spectra is, or our signal is making, or suppose our 90 degree pulse is not exactly 90 degrees. So, what we will get is signal which has a phase, with the x and y axis. In that case, your signal will not exactly like this one and this one, it will have slight phase shift, and your real image will look like this, your imaginary will look like this, imaginary part will look like this. So, Fourier transformation of this signal will look like this, and Fourier transformation of this signal will look like this. And in terms of your signal, it is basically the signal which we expect multiplied by exponential I phi, if this angle, this signal makes phi angle with the signal in x axis. Now, first thing you need to do is you have to do phase correction for this, and it is not very difficult to understand. What we need to do is we need to multiply the whole signal by exponential I phi correction. So, what do you do? That you multiply your signal by this factor, and when this phi corrected is equal to minus phi, you will get a signal which has been phase corrected. So, look at this, if there is 90 degree the phase, this phi value, then what you will get, this will become kind of sin modulated, this will become kind of cos modulated, and then Fourier transformation of this will look like dispersion, and Fourier transformation of this signal will look like an imaginary, the imaginary part will look like your absorption. And if you have a phi is equal to 180 degree, then real and imaginary will look like this. So, only thing is that the way we do phase correction is that you multiply by a correction factor which is equal to exponential I phi correct, and when you do that, then you can see the change in the shape of the real and imaginary part, real and imaginary part, and when this phi is equal to, for example, in this case phi is equal to 90 degree, then minus 90 degree, then what you will get is this exponential I phi correct into exponential I phi will be equal to 1, will be equal to 1, and or will be equal to 1, and then your exponential I phi correct minus phi, this will be equal to 0, and so exponential 0 is 1, and so your signal is now phase corrected. So, this is the way you do phase correction, and this is called first order phase correction. You also need to do second order phase correction. Sometime what happens that if you look at the Fourier transformation, you will get your signal at the last part of the spectrum, in one end of the spectrum like this, and to other part it will look like this, it will look like this. So, so if you notice here, this here notice here that phase changes are totally in different direction to the two ends of the spectrum, two ends of the spectrum, and for that you cannot multiply by a constant exponential phase function, you have to multiply something like this, multiply phase something like this, and when you do that, that is called second order phase correction. So, here is the negative part, here is the positive part. So, since here the phase is positive, phase is positive, and here phase is negative. So, positive part is multiplied by negative, whereas negative part is multiplied by positive. So, that now effect is so basically the correction is done at this, at phase phi is equal to 0, you see there is no correction needed, phi is equal to for this resonance no correction is needed, for this resonance no correction is needed. So, this is the way you do second order phase correction, and as I discussed in the initial lectures that NMR is low sensitive technique, and so we need to find a method to increase the intensity or signal to noise ratio, and the way we do is increase the concentration of analyte. So, it is not possible every time. So, second way is to increase the number of a scan, increase the number of a scan, collect the data in time domain mode and do Fourier transformation. These are the some of the way in which you can improve the signal to noise ratio. If I take n scan, then signal will increase to n times after n summed scans. Noise being random will contribute sometime positively, sometime negatively to the total noise, and so accumulation will be less rapid by root n times. So, if I take n scans, then signal to noise ratio gain by root n times. So, this we have already discussed. So, this is before acquiring the signal. Now, what we need to do is we can also do sensitivity enhancement when we are processing the data. So, these things need to be kept in mind when you are processing NMR signal, when you are processing NMR signal. So, here is the three cases. Here you see FID has been collected for longer time when, and here the FID collected for less time. If I do Fourier transformation of this spectrum, this FID, I will get signal like this, and if I Fourier transform this spectrum, we will get signal like this. So, if you look at this, there is more noise, whereas here is less noise. So, if you look at this NMR spectrum, what you will see that this part is quite long this part is quite long. What does that mean is, basically you are collecting more noise, because if you notice that signal is mostly contained in very small part, or what you say that all the signal is contained in early part of the FID. So, shortening the acquisition time will improve the signal to noise ratio. So, there is no need to collect all this FID, because the later part does not give any information. It basically increases the noise in the sample, increases the noise in the signal. And so, if I want to improve the signal to noise ratio, then I need to shorten the acquisition time, which is basically time spent in recording the signal. So, this is one of the way for sensitivity enhancement. Now, we know that signal is strongest at the start, and as the time progresses the signal decays and gets weaker, whereas noise remains at the same level. So, there are another thing which we can do for increasing the SNR or signal to noise ratio, that we should give more weightage to initial part of the FID. And so, the way we can do is that we multiply by a function which strongly decay with time, strongly decay with time. So, these functions are called window functions, and for sensitivity enhancement we should use a window function which is strongly decay function. What it does is that it will give more weightage to initial part of the FID and very less weightage to the later part of the FID. And one of such function is exponential function, and the window function for that is exponential minus R L B into T, exponential minus R L B into T. So, when you multiply by this window function, what it does is given in this scheme. So, this is the original FID. If I multiply by this function, what will it do? That you see this function after this part is 0. So, if you multiply after this, it will become 0. And again weighing is weight of this. So, suppose this is 5 and this is 5. So, basically if you multiply this, it will be 25. And if suppose you are here and here suppose signal is around 0.5 and suppose here this one is 0.5. So, 0.5 multiplied by 0.5, and so that can be given by 0.25. So, you see 5 is going to 25, whereas 0.5 going to 0.25. So, 5 is getting enhanced, where 0.5 is getting reduced. And so, what you basically did is that you gave more weightage to initial signals, whereas you are giving less weightage to the signal at the end. And if you do that, you will get this signal, and your weightage FID will be, if you multiply this by this, you will get this. This is weighted FID, and now you can see that how does this look like. Here almost all noise is 0, and when you do your Fourier transformation of this FID, you will get a very nice looking peak. You will get a very nice looking peak which has a less noise, So, in mathematic sense, what you are doing is you are multiplying this signal by weighing function, and this is your weighing function and this is your signal. When you do that, then S naught into exponential epsilon t exponential minus R L B plus R 2 into T. So, what you are able to do is, now your decay will going to be not only by R 2, it will be sum of R L B plus R 2. So, signal will decay very fast, signal will decay very fast. So, initially your signal decay by rate constant R 2, whereas now when you applied the weighing function, now signal is decaying by R L B plus R 2, and thus it leads to the signal to noise enhancement. Now, you are able to enhance the signal, you are able to enhance the signal, but that has a problem that basically compromises with the resolution, and now I will explain how. So, this is your FID which is decaying slow, and this is FID which is decaying faster than the first FID, and this decay very fast. If you do Fourier transformation, we will get a very sharp line for FID which is decaying slow, whereas a fast Fourier transformation of fast decaying FID will give a broad peak, and that I have already explained in my initial lecture why that happens, and that has to do with Heisenberg uncertainty principle. So, the a broad peak is obtained for fast decaying FID, whereas a sharp peak is obtained for slow decaying FID. So, for enhancement of signal to noise ratio, what we did, that we made our FID a fast decaying, but that leads to broadening of peak. So, sensitivity and resolution go in opposite way. So, if I increase the sensitivity, then resolution get lost. When I increase the resolution, your sensitivity get lost. A fast decaying FID has a less resolution. So, now question is, if suppose I want to do a resolution enhancement, what we need to do? We know that a weighing function designed to improve the SNR hastens the decay of signal, thus leading to broadening of line. So, for increasing the resolution, we need to multiply our signal by a weighing function which exponentially increase and thus delay the decay of the signal, and for that we use this weighing function, and now you can see this is exponentially increasing weighing function. So, weighing function is equal to exponential plus R RE into T, where RE is greater than 0. So, now we looked at how to increase the signal to noise ratio, how to increase the resolution, but if you apply window function which increase in SNR, it leads to your decrease in resolution. So, we need to find out an optimum where we can have best of both. For that, people design several different things. One of the function which has been designed is Gaussian function, where weighing function is exponential minus alpha t square. It is not exponential minus alpha t, it is exponential minus alpha t square. Let us look at this. Here is your FID and its Fourier transformation. If I multiply by this function, which is exponentially increasing function, then FID will look like this, and its Fourier transformation will give this kind of peak. Here signal to noise ratio is bad, but resolution is better, more sharp peak compared to this one. But you can see that here resolution increases, but SNR decreases. So, another way is to multiply by this function and then multiply by this function. So, one is increasing and another is your decreasing function, and that looks like here. So, initially it is, so initial part is it is increasing, where later part it is decreasing, and what it does is that it gives you this kind of FID, and that leads to this kind of frequency domain signal. So, here you have got an optimum level of the signal and resolution. So, this kind of things you need to keep in mind when you are trying to process your data. For example, if your peaks are quite separate, in that case you need maximum intensity, and so you apply a window function which gives you maximum sensitivity. If you can take higher concentration of the substance and peaks are quite nearby to each other, in that case it is easier to get signal to noise ratio, but you need a better resolution. In that case you apply a window function which enhances the resolution. But if suppose our spectra needs both sensitivity and resolution enhancement, then you need to multiply by weighing function which has this kind of feature. So, to get an optimum window function, sometimes people use sine Bell function. Sine Bell function can be of different type. Here is 0 degree sine Bell function with 0 phase, whereas this is sine Bell function with pi by 8 phase, this is with pi by 4 phase, and this is with pi by 2 phase. And again this can be applied keeping our use in mind. So, for example, here this kind of function 90 degree phase shifted sine Bell function is needed when we want to get higher intensity, higher signal to noise ratio, whereas this kind of function will be used if we want to take both signal to noise and resolution to optimum. If we want optimum signal to noise ratio and resolution, then we apply pi by 4 shifted sine Bell function. Sometimes we also apply sine Bell square function, and the shape looks like this. So, I hope now you understand how to apply the window function. It is very important because it will give it can affect your spectra. You can get your better resolution, or we can get better signal to noise ratio. The another thing which is important in processing of NMR data is what is known as zero filling. So, if suppose I take your NMR data for this many time for this acquisition period. So, basically you are taking these many data. If I take time acquisition and keep your number of data same, then you will get more number of data at this point, and if your T acquisition is small, and then you can get more number of data in this region. So, what zero filling does is that if you look at here, the FID along the top row has been supplemented with increasing number of 0, so contain more and more data point. So, here you can take more number of 0, and thus you can have more and more data point. So, Fourier transformation preserves the number of data points. So, the line in the spectrum is represented by more points as 0 are added to the end of the FID. So, if you take NMR spectra for this much time only and then add 0, then basically you are taking more number of data point in this period, more number of data point in this period, and which leads to more number of data in in your peak. So, in this FID remains the same for all 3 cases, no extra data has been acquired. So, this is about processing of data. So, 3 important things we discussed: how to correct the phase, the second thing we did how to improve the signal to noise ratio, how to improve the resolution, and if we want optimum resolution or optimum signal to noise ratio, then which kind of window function we need to use, and last is your zero filling. Last is your zero filling, and I told you what is the importance of this. Now, an NMR spectrum has chemical shift. So, if we are suppose you are applying your pulse at a particular ppm, so all proton will be excited. Now, question is if all protons are excited, whether chemical shift is going to be same. So, it is not so, because every nucleus is associated with circulating electron, and circulating electrons create a local magnetic field opposite to the direction of external magnetic field. Thus, a nuclei experience a smaller field than external magnetic field. In other words, spins are shielded from the external magnetic field. So, generally what you expect that nu is equal to 1 by 2 pi gamma b naught, but what happens, because every nucleus is associated with circulating electrons. So, these electrons will create a local magnetic field B E opposite to the direction of external magnetic field. So, what you are looking at is this frequency. Okay. So, spins are shielded from the external magnetic field by this your magnetic field, and so nu will be different for different nucleus, since B E will be different, for each nucleus. Shielding is proportional to external magnetic field. So, shielding is not constant, it also depends on external magnetic field, and B is given by sigma into B naught, and then frequency is 1 by 2 pi, this gyromagnetic ratio multiplied by B naught minus sigma B naught, where sigma is called shielding constant and depends on the structure of the molecule. And since sigma is different, and so different protons or protons in different environment will resonate at different frequency, and that can be used for the getting information about the structure of the molecule. So, chemical shift, what we come to know is frequency of absorption for 2 protons will not be same. It is important to note that frequency of the absorption will be different for same spin at NMR instruments with different magnetic strength, since delta E depends on B. So, another thing which need to be keep in mind, that frequency of absorption is going to be different for same spin. Even if you are looking at one spin, the frequency will be frequency of absorption will be different for that spin at NMR instruments with different magnetic field. For example, frequency will be different at 400 megahertz NMR machine, and frequency of that same proton will be different at 600 megahertz NMR machine, since delta E depends on B, and delta E will increase if I increase B, and so nu will be going to be greater. For example, if frequency of 2 protons lines at 400.0004 at 400.008 megahertz. So, if suppose 2 protons are there, one resonate at 400.004 and another resonate at 400.008 megahertz in 400 megahertz NMR machine, then these two lines will appear at 600.006 megahertz and 600.0012 megahertz in a 600 megahertz NMR machine. So, the spin which resonate at 400.0004 at in a 400 megahertz machine will now resonate at 600.0006 megahertz in 600 megahertz NMR machine. It is simple because in 400 megahertz machine this gap will be smaller, and then 600 megahertz NMR machine, since this gap is now bigger, and so nu in 600 will be greater than nu at 400 megahertz NMR machine. So, the separation between two lines is 400 hertz on 400 megahertz machine and 600 hertz on 600 megahertz machine. So, this signal, these two resonances, and the difference between these two is 400 hertz in 400 megahertz machine, whereas 600 hertz on 600 megahertz machine, exactly proportional to the magnetic field strength, exactly proportional to magnetic field strength. So, to keep the position of peaks same on two NMR machine, what we need to do? We need to normalize the position in NMR peaks. So, what we can do is we can simply divide this by nu. So, just keep this thing you see the normalized shift, let us write normalized shift is given by nu by nu ref, nu by nu ref. So, if we do that, then we will get one value. So, let us do it. When we do that, then normalization ensures that a peak which is at 400.0004 hertz at 400 megahertz machine and 600.0006 in 600 megahertz machine will appear at the value 1.000001 value, 1.00001. Frequency of a proton line at 400 point this will appear at 1.000002, and so you see the difference between these two is very small, 0.000001 hertz, or not hertz, it is unitless. So, 0.000001 hertz. So, difference in proton signal is very small and not convenient to express, and thus what we do is the position in NMR peak is not expressed in terms of frequency, wavelength, wave number, but in terms of chemical shift, and chemical shift is given by this value nu minus nu ref divided by nu of the reference material into 10 to the power 6. Nu ref is because nu of reference material into 10 to the power 6. Now, if we calculate spin 1 position in 400 megahertz machine, this is this minus 400.0000 divided by 400, and this will be 0.004 divided by 400, and if I multiply by 10 power 6, I will get 1 ppm, I will get 1 ppm. And so, this value is convenient to express, and that is why your in the NMR spectrum we take x axis in ppm, not in hertz as we do for other spectroscopy. So, first thing is that here the frequency is dependent on your external magnetic field, and that is why it needs to be normalized. Again the difference is very small, and so we need to get our x axis in terms of a number which is easier to express, and that is why chemical shift has been devised. The scale of chemical shift has been devised. There are a lot of factors which affect the chemical shift, few of them I am going to discuss in this. The first factor is electronegativity. The surrounding electron density of proton shields the nucleus from external magnetic field. Electron withdrawing substituent when attached to the same or an adjacent carbon de-shield proton, and resonance occurs at lower field or higher chemical shift. So, this is one thing which you need to remember, that electron withdrawing substituent de-shields proton and resonance occur at lower field or higher chemical shift value. So, you see here this is F, this is C, L, Br, Cl, this is I, this is I. So, CH3I, CH3R, and when electronegativity increases, what is means that it withdraws electron from carbon and just de-shields this hydrogen, and chemical shift is at higher position or lower field, higher position, higher chemical shift value or lower field. Chloride 3.0 to 4.0, if chloride is attached to CH3, proton will resonate between 3.0 to 4.0. If carbon is attached to bromine, these protons will resonate between 2.5 to 4.0, and similarly the case here you see R is your alkyl group, in that case your chemical shift value is going to be small. So, electronegativity is a factor which plays a role. The second factor is mesomeric effect. So, here you see this is your hydrogen attached to a double bond, its chemical shift is 5.29, chemical shift is 5.29, and when it is in resonance or mesomeric effect with the C double bond O, then its chemical shift value increases, and if the you see. So, what it does? It is taking away electron from this hydrogen, and that is why chemical shift is increasing. When the conjugation is in such a way that electrons is moving towards hydrogen, in that thing your chemical shift will be, in that case your chemical shift will be smaller. For substituted rings, again same way you can think of. So, a proton which is attached here, it comes at 6.55 because this electron is getting donated, and the effect will be more at this position, and at ortho position or para position if you take mesomeric effect into account. And so, these two protons has a smaller chemical shift than this proton at meta position. Same thing you can see when the substituent group is OMe or OCH3. If I have CH3 which is electron donating group, and then you can see that this value, if you compare between this and this value is higher. NO2 is electron withdrawing group, and now you see that this one has 8.21, this is 7.55, this is chemical shift 8.21, 7.55 and 7.70. Electron withdrawing group affects your this ortho position more compared to meta position and para position. The higher value of chemical shift will be for ortho and para, whereas for this meta the effect will be lowest, and so its chemical shift is smallest. So, today I will stop here. We will see the effect of other factors on chemical shift in the next lecture. Thank you very much.